This is a short video introduction to the Thermodynamics lab. It is a 2-week lab, so you have 2 weeks to complete. And it is an interesting lab that will combine many topics. So if you notice on the slide, it says read. And these are all the different sections of your book that tie into this experiment. So I would take some time to go back and review chapter 6.1 and 6.4, which is a discussion of enthalpy, delta H. Chapter 13.3, just the one section on temperature effects on aqueous solutions, how temperature affects solubility. Chapter 16.1 is about KSP, and I'm going to review that here in just a moment. And then chapters 17.1 through 17.4, which is the chapter that describes some new terms of delta S, which is entropy, and delta G, free energy. There's also a lot of background within the lab manual itself, or lab manual handout itself. So I would take a look at all those different sections and before you begin the lab, because I think that it will just be helpful to understand the key terms. There is going to be then the main purpose is going to be to relate KSP to thermodynamic values of free energy, enthalpy, and entropy. There's an Excel file provided that has data from previous course offerings. And there's also the lab handout, which is a modification of the lab manual that has instructions and guidelines on the calculations. And ultimately, you'll be turning in an Excel file with calculations and the answers to the questions that are asked, plus 2 graphs. So here's some information regarding the pre-lab questions. I won't give you the direct answers, but it's just here to guide you. We're going to be studying KSP, which is the equilibrium expression for salts dissolving. So here, KNO3 solid potassium nitrate is in equilibrium with its ions, and the K equilibrium is the solubility product constant. So it's the same K equilibrium, products over reactants, but it's specific to describing solids that are in equilibrium with their ions. And that is, so if we think about, here's a beaker with potassium nitrate as a solid, and then ions going into solution. This is an equilibrium process, and the KSP describes that situation where you have solid present and also the ions present. Now, if you recall from our discussions of K will be the ratio of products over reactants, but we do not include solids in our K expression, so that's why it's absent from here. So the first thing that I'd like you to think about is, what would we expect for the magnitude of KSP since the salt is soluble? And how do you know it's a soluble salt? Because hopefully you remember from Chem 200 that all nitrates are soluble, right? So the question here for you to think about then, if a salt is soluble, would you expect K equilibrium to be, KSP, to be less than 1? Would you expect it to be greater than 1? Or would you expect it to be around 1? In other words, do you think the equilibrium favors the ions or the solid? Okay, the next pre-lab question is to think about enthalpy. And enthalpy is heat at constant pressure. And it refers to the differences in heat energy between reactants and products at constant pressure. So the terms that you're familiar with enthalpy are endo and exothermic. So one thing to think about is for the dissolving of KNO3, based on your previous knowledge of chemistry, would you expect that to require heat to dissolve or release heat, and why? And one of the things you can look at would be to read the section from chapter 11 that was outlined earlier on temperature effects and solubility. So this is kind of the overarching idea. Temperature effects. How does temperature affect the solubility of an ionic compound? Okay. The next pre-lab question is referring to a new term, which is called entropy. And this is chapter 17 material. And it is the energy that's associated with the dispersion of atoms and molecules. And what we want to think about as we're looking at our equation, which is potassium nitrate solid in equilibrium here with its ions, would be what would we expect for the change in entropy? Now, if we see a positive change in entropy, this is for our system, which is the reaction we're studying. Positive changes in entropy usually lead on a molecular level to a greater number of microstates, different possibilities for how those molecules can arrange. Whereas if we see a decrease in entropy, we'd see a decrease in the number of microstates or arrangements on a molecular level. And so with this idea, then we tend to associate the idea of entropy with randomness. So if we see an increase in the number of microstates, that system has gone towards a more random state, and the entropy change would be positive. Whereas if the entropy of the system's negative, it's a decrease in the number of microstates or probabilities for those ions or molecules to arrange. So it'd be less random. And so the question to you will be, would you expect when an ionic solid dissolves to form free-floating ions, what would you expect the sign of the entropy to be, positive or negative? And then our last thermodynamic discussion is on delta G, where G stands for Gibbs free energy. When delta G is negative, the process is favored and will take place without outside intervention. And so that process is occurring spontaneously. So when potassium nitrate dissolves in water, are you expecting that to occur without outside intervention when you throw that salt into water? And so the question here is, based upon what you know about the solubility of nitrate salts, do you think that process is spontaneous? Do you think its delta G is negative? Okay. From chapter 6, I believe it's 6.4, and then 17.1 through 17.4, those chapters, you learn how to write the theoretical values for delta H, delta S, and delta G. So one of them got deleted from here. Sorry about that. Okay, so this one's for the enthalpy. Now don't be too nervous about this because this is pretty simple. That we're going to use thermodynamic tables in the back of your book. So the appendix, I believe it's appendix 4. Hold on a second. There are thermodynamic values that you can, yeah, it's appendix 4. That for most any process, you can look up the values for delta H of formation. And if you take products minus reactants, you can come up with delta H of reaction. The N here would be the number of moles, and I'll do an example of this in a second. So for our 3 thermodynamic values that we're discussing, enthalpy for the first one, entropy and free energy, then we can find the delta H of those reactions, delta S, delta G's, using thermodynamic values that are in the back of your book. Now, in the case of this particular reaction that we're studying, oh, there it was. So it was there. I just had to click on it. Oops, I'm highlighting. Okay, so there it is. It's a much nicer writing. Okay, so we can find those theoretical values. Now, for our process that we're studying, which is potassium nitrate, solid, forming its ions, not all of the values are back there. And so for that reason, we're going to find the theoretical values for these from this particular reference chart that's given in the lab manual handout. So let me just show you how it would work on one of them, and then you can do the other ones later as part of your lab. We would look at our balanced equation up here, and then I'm going to take products minus reactants and include the coefficients. So I would take for delta H of this reaction would be product, which would be potassium ion. Oops. So that's kilojoules per mole. We have 1 mole of the potassium ion, so that's going to cancel. And then we have nitrate. Okay, so those are our products. And then we'd subtract off our reactant. So these all are 1-to-1 mole ratios here, right? They're all ones. But if they weren't, then we would adjust for that. And so I'll let you finish that off, but that's going to give you the enthalpy for this process. You do the same thing for delta G and delta S. And then these would be considered our theoretical values. Okay, so that's easy enough. Now, as you do your lab, you're going to have an Excel file you should have open, and you should have the lab manual handout. It's a handout. It's been modified for our new format. So there's going to be within that document, it's going to say, hey, calculate this, but put it into the table 6, table 1, table 3 to kind of help you organize your numbers. So in this case, once you determine the delta H theoretical, delta S, and delta G based on these thermodynamic values here, products minus reactants, you will put those numbers into table 6 of the Excel file that's provided. Okay, so as you know, we're not physically doing the lab, but I will describe to you what the lab would have been like. Now, here's the interesting point. If you took Chem 200L at Mesa, you have done this experiment. It was actually, I think, experiment 13, the very last one you did in 200L. Some people may not have done it because sometimes you can drop an experiment, but anyways, you might have done this one. So what it is you're going to take potassium nitrate solid and essentially dissolve it in water. Potassium nitrate is an irritant and oxidant. So normally you'd wear your safety goggles, and then if you got any on your skin, you would wash it thoroughly. Okay, so what we would have done, would have taken a hot plate, a really large beaker. Then we'd have a burette. So here's the burette, and that's going to have water in it. So you're going to put water. And the reason why we need the burette with water is that it's going to tell us how much we're adding. And then you're going to have a graduated cylinder. And within the graduated cylinder, you're going to weigh out approximately 20 grams of potassium nitrate. Okay, and then the burette, you'd add the water into that cylinder. Okay, and then the cylinder, the graduated cylinder, would get dropped into this water in the giant beaker that's heated. Okay, so we're going to weigh about 20 grams out in the weighing boat. You add the potassium nitrate to the graduated cylinder. The burette has the water. And then to the burette, you're going to add about 50 mils of water. And then you're going to heat this up. Okay, you're going to heat it until the solid's dissolved. And then you're going to take it out of the hot water bath and let it cool, but keep stirring it. Okay, so you're going to keep stirring it once you pull it from the hot water bath. And then here's the important part, is that you want to note when the first crystals appear, because really what we're trying to get is we want what's called a saturated solution, where you have ions present in there. So here's the graduated cylinder, where you have solid present. So I'm going to do a little flaky crystal because you don't want a lot. You want that first point where it forms. And you have ions in there with it. So that's what we call a saturated solution, where you have the solid in equilibrium with the ions. Okay, so as soon as the first crystal appears, it's going to look like a little flake. You're going to record that temp. And you're going to read the volume of the solution in the graduated cylinder. Okay. Crystals forms pretty quickly when they start to form. They're kind of hard to see because they're very tiny little snowflake-like pieces. Okay. So once you took one of the temperature readings, then you do this 2 more times, right, to repeat it. So you redissolve the crystals in a high temp. Then you take it back out again and watch the solid. That point where you see that one flake is caught as early as possible. That's the formation of the potassium nitrate solid. Okay. All right. Then you're going to add 5 more mils of distilled water, and you're going to reheat it till it redissolves again. And then you take it out again, let it cool, and then once again find that point, that temperature at which potassium nitrate forms as a solid. Okay, and then you do that another 2 times to confirm what you've seen, so to reproduce it. Okay. And you want to try to allow the solution to cool slowly. Okay. And then you do it twice to reproduce it. Okay. Okay, so if you were doing this, you'd repeat the above procedures for a total of 3 different equilibrium determinations, 3 times at different volumes of DI water that's added. Okay, and we'd have to record all the volume and temperature measurements. And we'd also have to remember that we wanted to note the temperature at which those crystals first appeared. Okay. Now, it was hard to find a really great video for this. This one here that's highlighted, it's okay. It kind of goes through the experimental procedure. It's pretty short. It has some very like dramatic kind of Star Wars music in the background, but if you want to kind of see what it would have looked like, go ahead and click on that. Okay, so I want to go through some of the calculations with you, but this is all described in the lab manual handout that your instructors have posted on Canvas. And so, you may or may not need this. I just wanted to go through it with you to kind of show you what kinds of things to think about as you are working the calculations. So you're going to be given a really nice looking Excel file, and this is the same picture of it. It's just a different color. So in it, you have data from a previous class. So the first thing that you should note is that the original mass of the KNO3 was around 20 grams, but of course we would have its actual mass, right, to 4 decimal places. There you have the molar mass of KNO3. So your first thing that you're going to have to calculate is the number of moles of KNO3 that you dissolved in there. Okay, here's our trial number 1 here. The amount of water approximately added is 15 mils, but the actual amount is what we read from the burette. So initially it's 0, but then the final burette reading is 15.05. So the amount delivered that eventually you'll type into the Excel file is 15.05. Okay. This was done 3 times. So 3 times it was heated up and allowed to cool until that little crystal structure appeared, and then the temperature was recorded. So the first temperature was 66.0, second one was 66.3, the third was 66.8. So you'll need to go ahead and average those 3 to get our temperature average. Okay, the one thing I want you to note that I think is important so you're not confused is that sample stays, but then you're going to add approximately 5 more mils of water. So the final volume goes up to somewhere around 20 mils. So that, and then for the next one, for the third trial, you're adding 5 more mils for a final burette at around 25. So keep that in mind, that was the experimental setup, is to add for each trial 5 more mils of water. Okay, and then the temperature at which the crystals form changes because the concentration of the salt changed, right? You have the same amount of KNO3, but the molarity is different. Okay, so now the question is, we need to find KSP. So remember, KSP is the K equilibrium for the dissolving process of the salt. And it is found at that point where the solution's saturated, where you have ions and solids. So it's at that point, again, where you have that crystal structure form, and then you have the ions in there as well. So that is the equilibrium spot. Okay, so for this part of the calculations, you were going to, in the previous table, you'll have your average temp, right? So this is going to be from table 2. And then now the question is, how are you going to find your concentration? Well, you have your moles of KNO3, right? And then you have your total volume. You have your total volume of solution. And of course, for molarity, that needs to be in liters. So let me see if I can go back to my previous slide. The total volume for this solution here, this was recorded by the graduated cylinder where you had the potassium nitrate solution. Okay, so you have a certain number of moles of KNO3, and you added, let's say in that first one, 15.05 milliliters. But of course, the solid takes up some room, right? So the volume's going to be bigger. And here's that number from the student's data. It's in milliliters. Okay, so for the next one, then that number is the number that you need here. That's the total volume, not just the amount delivered. Okay, and that's going to give us our concentration. I'll give you a hint because the lab manual handout gives you a hint that normally we get somewhere around 8 molar for that first number. Okay, next up, KSP here. So our KSP is really an ice chart. Where you have some solid and it is ionizing to some extent. And so we'll call that amount of solid minus X plus X plus X. But recall that the solid won't appear in the K expression. So KSP is the concentration of potassium ion times nitrate. So once we have the concentration, which I said was going to be around 8 molar, we would just plug those numbers in. Now let me stop here for 1 second, just to be more thorough, is that when it comes to KSP, we switch out the X and we call it S for the solubility. So when you see this in your book, these will be S's, but it's still the same idea that it's the X amount, the amount of ions. So KSP will equal S squared, where S is the concentration. So hopefully you're thinking that if my first value is going to be around 8 molar, then our first KSP would be 8 times 8, which usually we get somewhere around 64 for that one. Okay, so that's our first part, is finding KSP. Then what it's going to ask you is to relate this back to some information that you learned in Chem 200, which is the idea of solubility. So for this, if you could go to that section in chapter 11 that I highlighted, which I believe is 11.4, of temperature and its effect on solubility. Hopefully you remember that most salts, if we increase their temp, you're going to increase their solubility. That's true for most salts. There are some exceptions, but for the most part, this is the case. So what we're going to do here is, using the data we've collected, is express the solubility of potassium nitrate in grams of KNO3 per 100 grams of water. Okay, so how are you going to do that? Is you're going to go look at your data and you're going to take the mass of the salt, right? You're going to take the mass of the salt. Oops, sorry, I meant to go backwards. We have the mass of the salt as 20.236. Need to write that down as we go forward. 20.2364 grams. And then the amount of water was 15.05 grams. Okay, so 20.2364 grams of the salt in 15.05 grams of water. So the question's going to be, how many grams would dissolve in 100 grams of water? So that's going to express our solubility for that one. Okay. And so you can go ahead at those different temperatures, because you have different temperatures here, is to determine the solubility per 100 grams of water. And then what it's going to ask you to do is, once you get that information, is to plot the solubility versus temperature in degrees Celsius. Now, we are expecting that the greater the temp, the higher the solubility, so that this should go up. This should be an upwards trend. Okay, so the other thing that it will ask you in your lab manual handout is that once you've generated that graph, and you're going to make it look nice with its units, its axis, its titles, all on one nice page, very professional graph, then it's going to ask you to compare it to the known graph for potassium nitrate. And I'll give you a hint that it is found in your textbook in chapter 11. And or also you could look it up on the internet, because the solubility versus temperature of salts is a very common graph. Okay, very easy to find. Okay, now there is one thing that I kind of glossed over kind of quick, is that this 15.05 was originally in milliliters. And I went quickly to convert it over to grams of water. I did that because the density of water is 1 gram per mil. Now, as you know, the density of water will change with temp. So your lab instructor may want you to use a more precise value for that. I do believe that I normally have my class use 1 gram per mil, but you can ask your lab instructor what they'd like you to do with that. So if I delivered if I delivered from the burette 15.05 mils of water, then because the density is 1 gram per mil, that is 15.05 grams of water. Okay, so that's the first part. Then what we're going to do is we're going to figure out what's called delta G from equation 1. And that particular calculation is that delta G's relationship to K is through the equation negative RT ln K, and I'm just going to put SP because that's the one we're studying here. This is a really important equation because what it's telling us is if K is greater than 1, so if you have a product favored reaction, then delta G will be negative and that process is spontaneous. So if K is much larger than 1, that is telling us that it's product favored. So K is greater than 1. It's product favored. And delta G will be negative. Okay, and so we'll see, we're going to predict that that's probably going to be the case, right? Because nitrate salts dissolve spontaneously, but we're going to show that experimentally with our numbers. Okay, if KSP were less than 1, it'd be the opposite. Delta G would be positive and not spontaneous. And if KSP were exactly 1, then delta G would be 0. Okay. Okay, so you're going to have to calculate your delta G values. And then the last part of the lab is the following. So let's see if it's on the next page. If not, I'll come back. No. Okay, so what we're going to do is we're going to find our other thermodynamic values of interest were enthalpy and entropy. And the way that we can find those is by generating a graph. And I think I will click on to the next slide. What we're going to do is you're going to plot, well, you're going to have KSP at your different temps in degrees Celsius. Okay, now that relationship won't be linear. So the relationship that's linear is ln KSP versus 1 over temp in kelvins. Now, one of the things that you've learned from your chemistry labs is that we can generate linear relationships by converting the data sometimes to ln, log, reciprocals of temp. Okay, and in that case, that's true. So in this case, that's true. So on the previous chart, I'm going to hit previous. You're going to have your average temperatures, okay, for when those crystals appeared. You're going to convert to Kelvin. You're going to convert to reciprocal Kelvin. And then you're going to have your KSP values, right? I'll double star it. And then you're going to take ln KSP of those. So now you're going to have ln KSP and 1 over T. And what's that going to do is we're going to generate a graph. Here's a nicer picture of ln. I don't know if I can write it sideways. Let's see. ln KSP versus 1 over T. And Then you're going to do that on Excel, right? And you're going to generate an equation of the line. And you're going to tell Excel to generate an equation. You're going to get the numbers that are appropriate. Okay. And one of the equations that's given in your lab manual is that there's this relationship that's known. Okay, so this is given. And I'm sorry, I'm so used to writing little k. I by default went there. Big K. KSP. Okay, so what is this equation telling us? Well, first of all, it's saying that ln KSP versus 1 over T in kelvins is a linear relationship. Y equals mx plus b. And the other thing it's going to allow us then to do is that the slope is going to equal negative delta H over R. And so this is an experimental way for us to find the enthalpy. Okay. I asked you to predict what you think. I asked you earlier, do you think it's going to be endo or exothermic? Here we can calculate it and see if we get it as an endo or exothermic. The intercept, the y-intercept here is delta S over R. So we can find the entropy, the delta S value. Okay, how are you going to do that? It's just algebraically, right? If the slope, for example, is equal to negative delta H over R, delta H equals negative M times R. And this is the R, that's the 8.314 value. So you'll see that in your manual. The y-intercept is delta S over R. And so we can solve for that one by multiplying the intercept value times R. And so we're going to have experimental delta H and experimental delta S. Okay, and so those would be both determined from the slope and intercept. Okay, and then from that, we can find the delta G values. So delta G will equal delta H minus T delta S, and we're going to be asking you to give that to us at 25 degrees, which is 298.15 Kelvin. Now, if you think back where we started our lecture, I asked you to determine the theoretical values based on doing products minus reactants with the known thermodynamic values. So you'll have those in table 6. And so you're going to take a percent error between experimental and theoretical. So you're going to compare experimental versus theoretical. Okay, so that's a lot of information, and that's why I recommended that you did your reading on it first. So especially 17.1 through 17.4, but you do have 2 weeks to do this. So you can do your reading, come back and re-listen to this, and then go ahead and try to tackle the data. So all of it should be in the Excel files, the easiest thing. Put all your calculations in there. Any questions you can type in there. and then you'll generate the two graphs, one for the solubility of the salt, and the other one is this one, ln KSP versus 1 over T.